Project Firework, aka Experiments with Compose Hot Reload, reached a massive milestone. Not only is it already in use for the development of the Kotlin Conf 2025 app, but other teams inside and outside JetBrains claimed that they started offering this developer experience to their engineers or are planning to. Most important though, the repository was officially transferred to the JetBrains GitHub account and the experiments continue. And there were a lot of experiments already and plenty of lessons learned. One of the lessons is a tale about ClassLoaders, their elegance, simplicity and almost unmatched power when it comes to reloading code on the JVM. Initial prototypes and demos using this approach looked really promising and motivated several people inside JetBrains to push me further, trying to see if this idea could become a JetBrains maintained technology. In the end, while a class loader based approach was the spark igniting Project Firework, the approach was deemed infeasible as a core Kotlin or Compose technology. We will see later why. But now let's explore how this works and how you could theoretically build something very similar for you today. If you flinch when you hear the word class loader, then don't worry. For most of my career, I was scared to death of class loader issues. Once you see a class foo cannot be cast to class foo kind of issues, then you bet that your disappointment is immeasurable and your day is ruined. But once we try understanding class loaders, then it becomes immediately obvious how one might be able to implement hot reload with them. Let's start with the obvious. You know that classes in Java do have a fully qualified name, FQN, for example Java long string or java.io.file or even kotlin.result. The fun part is that now at runtime these FQNs can actually live in separate namespaces. Class loaders are such namespaces. It is indeed possible to have two classes called happy.foo in separate namespaces, aka class loaders. Notice that those class loaders do actually have a parent-child relationship. When the JVM is looking for a class inside a given context, then a class loader can try to look up classes from their parent class loader. Since we can create such class loaders in our application dynamically, how about separating our application code into cold and hot reloadable UI? Now, after we changed our code, recompiled the class files, we could create a new namespace with the new code and rerun Compose, which should re-render the UI. Let's look into actual code. The separation between cold application and hot UI code is strictly necessary. If the entire app is reloaded and re-executed, then there's not much state left and we just implemented a glorified rerun. Therefore, user code has to be separated into two source sets, two compilations. Let's use the main source set, the main compilation for regular cold code, and introduce a new UI compilation to put all the hot reloadable UI code in. When launching the application, we can provide two sets of files. This prototype will set two system properties, classPath.cold and classPath.hot. Our demo app defines a simple main composable function in the common UI source set. This composable will use state defined in JVM main and increment a counter value when a button is pressed. Now let's look into how the class loader is created or recreated and how we then re-render the UI. We can start by looking into the actual main function used to start the application. Other than using my library efas, it looks like an almost very typical Compose desktop app. We create an application with a single window, nothing too interesting except this link UI function, of course. This link UI function is provided the name of our UI.kt class. After reading the classPath.cold and classPath.hot properties, it can create the cold class loader. Changes to the hot class path can be watched inside a launched effect, watching the known class files which can change. Every time the class path changes, this reload method can be invoked, which then creates a new hot class loader and resolves the UI.kt class. The UI will then react to the new class being available and reactively invokes the UI. Let's try it out. We can start the application, and with a Gradle daemon recompiling the project in the background for us, we should be able to switch the behavior of our button from decrementing the counter to incrementing and back while not losing any of the application state. It seems like recreating new class loaders works fine, right? And indeed, creating a new namespace is almost like creating a new universe in the JVM, and you can basically rerun arbitrary code. Similar techniques are used for rendering previews in IntelliJ or Fleet. But if this approach is so great, why was it then rejected for Project Firework? You see, for such an approach to work, a lot of care needs to be taken by the actual application developer. It is required to refactor your code, strictly separating the UI from the rest of the application. And even when this price was paid, too many pitfalls might be ahead of the application developer, which would require extensive knowledge about the JVM and could become very frustrating. Just leaking any objects from the UI code into non-UI code, for example by sending events or defining custom state, will likely cause class cast exceptions being thrown left and right, so this approach is very, very powerful, but the price is too high. If you're interested in learning how Project Firework is actually implemented at the moment, make sure to watch upcoming videos. Thanks, and as always, have fun with Kotlin.